Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the strange tale of a visitor from the void, Comet 3 I/Atlas, and its peculiar, broken symmetry. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. In the outer reaches of our solar system, where sunlight arrives as little more than a distant whisper, something ancient stirs. The interstellar Comet 3 I/Atlas drifts through space at 17 kilometers per second, carrying within its frozen heart the chemical memory of another star system entirely. Its nucleus, perhaps 3 kilometers across, tumbles through the darkness like a cosmic pebble, unremarkable in size, extraordinary in origin. This wanderer has crossed the vast emptiness between stars, a journey that spans not years or decades, but geological epochs. The mathematics of interstellar travel reveal the profound loneliness of 3 I/Atlas's journey. At 17 kilometers per second, a velocity that would circle Earth's equator in 40 minutes, this comet has nonetheless required millions of years to traverse the space between stellar systems. For most of its existence, it has known only the cold embrace of the interstellar medium, that tenuous soup of hydrogen atoms and dust grains that fills the space between stars. The nearest star would have appeared no brighter than Venus appears from Earth, a brilliant point of light offering no warmth across the cosmic distances. The comet's surface bears the accumulated scars of this interstellar odyssey. 4.5 billion years of cosmic ray bombardment have altered its chemistry at the molecular level, creating a weathered rind of complex organic molecules, high-energy particles, protons accelerated to nearly the speed of light by distant supernovas and stellar winds, have struck the comet's surface billions of times per second throughout its journey. Each impact breaks chemical bonds, rearranges molecular structures, and slowly transforms the original ice and rock into something subtly different. Beneath this darkened, radiation-processed crust lies pristine ice, water frozen when our solar system was still forming, when the sun itself was merely a collapsing cloud of gas and dust. This ice remembers temperatures barely above absolute zero. The profound cold that exists in the vacuum between stars where no stellar radiation can reach. In its crystalline structure lies encoded the thermal history of another world, another time, another region of the galaxy entirely. The ice formed around dust grains that condensed from the atmospheres of dying stars, carrying within its molecular matrix trace elements forged in stellar cores and scattered by supernova explosions. As 3 I/Atlas approaches the inner solar system, crossing the invisible boundary where Mars traces its elliptical path, the sun's influence begins to assert itself with gentle persistence. Solar radiation, though still faint at this distance, less than half the intensity that reaches Earth, begins to penetrate the comet's dark surface. Photons that left the sun's surface 8 minutes earlier and traveled 200 million kilometers strike the ancient ice at wavelengths ranging from visible light to infrared heat radiation. The first molecules of water vapor begin their escape, not in dramatic jets or explosive bursts, but as a gentle molecular exodus that unfolds with the patience of geological time. Individual water molecules, their hydrogen bonds weakened by solar heating, break free from the crystal lattice that has held them for eons. They rise slowly through the comet's tenuous atmosphere, accelerating as they move away from the nucleus's weak gravitational field. This process, sublimation, represents one of nature's most elegant phase transitions. Ice transforms directly to vapor in the near-perfect vacuum surrounding the comet, bypassing the liquid phase entirely. Each escaping molecule carries away a tiny amount of heat energy, approximately 2,800 joules per gram, cooling the surface even as solar energy attempts to warm it. The comet breathes out its ancient substance in slow, measured exhalations that will continue for months as it journeys deeper into the solar system's gravitational well. The rate of sublimation increases exponentially with temperature according to the Clausius-Clapeyron equation, a relationship that governs phase transitions throughout the universe. As the comet warms from -200 degrees Celsius to -180 degrees Celsius, the sublimation rate doubles. Another 20-degree increase doubles it again. This exponential relationship means that small changes in solar heating produce dramatic changes in comet activity, a sensitivity that will prove crucial in understanding the asymmetries that develop later. The escaping gases drag with them microscopic dust grains, particles of silicate minerals and organic carbon compounds no larger than cigarette smoke. These motes of matter, liberated after eons of frozen captivity, begin their own journey away from the nucleus. They move slowly at first, barely faster than a gentle terrestrial breeze, accelerating as they travel outward into the growing coma of gas and dust that surrounds the comet's heart. The largest dust particles, perhaps a millimeter across, move most slowly. The smallest, measured in nanometers, are swept away rapidly by the expanding gas. The ratio of gas to dust in the escaping material reveals details about the comet's internal structure and composition. Too much dust suggests a fragile nucleus prone to fragmentation. Too little indicates ice so pure it lacks the rocky components typical of solar system formation. 3I/Atlas produces dust and gas in proportions that seem familiar, yet subtly different from native comets, a hint of its exotic origin that will become more apparent as observations continue. Scientists observe this awakening from Earth through telescopes scattered across continents and orbiting in space. Their instruments, sensitive enough to detect individual photons after their journey of hundreds of millions of kilometers, train on the faint smudge of light that marks 3I/Atlas's position against the star field. The comet appears as little more than a fuzzy star to casual observers, but sophisticated analysis reveals a wealth of detail about its structure and behavior. Spectroscopic analysis dissects the comet's light into component wavelengths, revealing the familiar molecular signatures of water vapor, carbon dioxide, and carbon monoxide. Each molecule absorbs and emits light at characteristic frequencies, creating a unique fingerprint that astronomers can read like a chemical recipe. The spectra show not just what molecules are present, but their temperatures, velocities, and relative abundances, a complete inventory of the comet's gaseous envelope. Yet even in these early observations, subtle anomalies emerge that hint at the remarkable phenomena to come. The comet's brightness variations don't follow the smooth curve predicted by standard cometry models. Instead, there are irregularities, small deviations that suggest the nucleus is not uniformly active across its surface. Some regions outgas more vigorously than others, perhaps because they contain more volatile ices or because their surface structure allows deeper penetration of solar heat. The mystery of 3I/Atlas deepens with each passing night of observation, each spectrum analyzed, each image processed. What begins as a perfectly ordinary awakening of ancient ice will soon reveal itself as something far more intriguing, a phenomenon that challenges fundamental assumptions about how comet tails form and evolve in the solar wind. The transformation accelerates with the quiet inevitability of physics itself. As 3I/Atlas continues its inward journey, crossing the orbital distance where the asteroid series traces its lonely path, the Sun's influence penetrates deeper into the comet's ancient structure. The surface temperature rises from negative 180 degrees Celsius to negative 160 degrees Celsius, a change that seems modest by terrestrial standards, but represents a doubling of the sublimation rate according to the exponential laws that govern phase transitions in the vacuum of space. Water molecules escape the nucleus with increasing frequency now, their liberation following patterns established by the comet's slow rotation and the uneven distribution of volatile ices beneath its weathered crust. Each molecule that breaks free from the crystal lattice takes with it the energy of sublimation, cooling the immediate surroundings while contributing to the growing envelope of gas that surrounds the nucleus, like an atmosphere measured in thousands of cubic kilometers, yet thinner than Earth's air at a height of 100 kilometers above sea level. The process unfolds with a precision that reflects the fundamental constants of nature. The binding energy of water molecules in ice, 51, 8 kilojoules per mole, determines exactly how much solar heating is required to break the hydrogen bonds that have held the comet's substance together since its formation in another stellar system. The Stefan-Boltzmann law governs how efficiently the nucleus radiates heat back to space. The Maxwell-Boltzmann distribution describes the velocities of escaping gas molecules, with faster molecules preferentially escaping the comet's weak gravitational field, while slower ones may fall back to the surface in a gentle rain of condensation. Carbon dioxide ice, frozen at temperatures below negative 78 degrees Celsius, begins to contribute its own molecular flux to the expanding coma. Unlike water, which requires significant heating to sublimate, carbon dioxide transitions directly from solid to gas at temperatures the comet experienced even in the outer solar system. Its molecules move faster than water vapor, their lighter molecular weight allowing them to achieve higher velocities for the same thermal energy, and they escape the nucleus more readily, carrying with them dust grains that might otherwise remain gravitationally bound. The dust component of the coma reveals the comet's internal architecture with each passing day. Silicate grains, fragments of minerals that condensed from stellar atmospheres billions of years ago, emerge from the nucleus embedded in a matrix of organic compounds darkened by eons of cosmic ray bombardment. These particles range in size from molecular clusters of a few dozen atoms to microscopic chunks approaching a millimeter in diameter. Their distribution follows a power law, with small particles vastly outnumbering large ones in a pattern that reflects the fractal nature of grinding and fragmentation processes that have operated throughout the comet's history. Spectroscopic observations reveal unexpected complexity in the escaping gases. Alongside the dominant signatures of water, carbon dioxide, and carbon monoxide, weaker spectral lines hint at the presence of methanol, formaldehyde, and hydrogen sulfide, molecules that formed in the reducing environment of the interstellar medium where 3I/Atlas originated. These trace constituents provide a chemical fingerprint of conditions in another part of the galaxy, a stellar nursery where temperatures and pressures differed subtly from those that prevailed during our own solar system's formation. The comet's brightness increases by factors of 10 as more surface area becomes active, and the production rate of gas and dust accelerates exponentially with warming. What appeared as a faint smudge through small telescopes weeks earlier now presents a distinct coma visible through binoculars from dark sky locations. The expanding gas cloud reaches dimensions of 100,000 kilometers across, larger than the planet Jupiter, though containing less mass than a small asteroid. Professional astronomers tracking 3I/Atlas notice that its light curve, the graph of brightness versus time, shows systematic deviations from the smooth progression expected for a uniformly active nucleus. Instead, the brightness varies with a period of 7.3 hours, matching the comet's rotational period as determined from earlier observations. This periodic variation suggests that different regions of the surface have different levels of activity, creating a lighthouse effect as the nucleus spins and presents alternately active and dormant faces to solar heating. The pattern of brightness variation reveals clues about the nucleus's shape and surface properties. If the comet were a perfect sphere with uniform surface composition, its brightness would remain constant as it rotated. The observed variations indicate either an elongated shape that presents different cross-sectional areas to the Sun, or non-uniform surface activity where some regions produce more gas and dust than others. Detailed photometric analysis suggests both factors contribute. 3I/Atlas appears to be somewhat elongated, perhaps twice as long as it is wide, with distinct regions of high and low activity across its surface. The physics of gas expansion from the nucleus follows principles established by kinetic theory and fluid dynamics. Near the surface, the density of escaping molecules is high enough that they collide frequently with each other, creating a hydrodynamic flow similar to gas expanding from a nozzle, further from the nucleus. As the gas density drops, molecular collisions become rare, and each molecule follows its own ballistic trajectory under the influence of solar radiation pressure and the weak gravitational fields of the Sun and planets. This transition from hydrodynamic to ballistic flow occurs at a distance of roughly 100 kilometers from the nucleus, a boundary that marks where the comet's behavior shifts from gas dynamics to celestial mechanics. Within this inner region, the temperature and velocity of the expanding gas are governed by thermodynamic principles. Beyond it, individual molecules follow Keplerian orbits modified by radiation pressure, creating the complex particle dynamics that will eventually shape the comet's tail. The escaping gas carries away angular momentum as well as mass, exerting a subtle torque on the nucleus that can alter its rotational period over time. For 3I/Atlas, with its modest size and rotation rate, this effect remains negligible compared to other forces acting on the comet, but the principle illustrates the interconnected nature of cometary phenomena. Mass loss affects rotation. Rotation affects the pattern of outgassing, and outgassing determines the structure of the coma and the eventual tail. Ground-based observers begin to detect the first hints of directional structure in the coma, subtle asymmetries that suggest the gas and dust are not expanding uniformly in all directions from the nucleus. These early signs of departures from spherical symmetry appear as slight elongations in the coma's brightness distribution, barely detectable without careful image processing and statistical analysis. To the untrained eye, 3I/Atlas still appears as a simple fuzzy star, but sophisticated instruments reveal the beginnings of the complex phenomena that will soon transform it into one of the most studied objects in the solar system. The comet continues its inward journey with the patient persistence of gravitational dynamics. Its orbit, determined by the mass of the Sun and the laws of celestial mechanics that govern all motion in the solar system, each day brings it roughly 1.5 million kilometers closer to the Sun. Each hour sees its surface temperature rise by fractions of a degree. Each moment witnesses the escape of billions of molecules that have waited eons for this liberation from their icy prison. Only now do the subtle asymmetries in gas production begin to assert themselves more strongly, setting the stage for the remarkable tail structure that will soon develop. The gentle, nearly spherical coma represents the last stage of symmetric behavior from this point forward. The comet's evolution will be dominated by directional effects that create the spectacular asymmetric tail that gives 3I/Atlas its place in the annals of astronomical discovery. As 3I/Atlas approaches the orbital distance of the asteroid belt's inner edge, where temperatures rise above the threshold for sustained water sublimation, the escaping gas begins to drag microscopic dust grains away from the nucleus in a process that unfolds with the inexorable precision of molecular physics. These particles, fragments of silicate minerals, organic compounds, and metallic oxides that formed in the atmospheres of distant stars billions of years ago begin their own independent journey through the solar system. each grain following a trajectory determined by its size, density, and the complex interplay of forces that operate in the vacuum of space. The dust grains emerge from the nucleus embedded in jets of expanding gas, their initial velocities tied to the hydrodynamic flow of sublimating ice. Water vapor molecules, moving at average speeds of 500 meters per second at the temperatures prevailing near the comet's surface, collide with dust particles and transfer momentum through countless microscopic impacts. The smallest grains, measured in nanometers and containing only thousands of atoms, are accelerated rapidly by gas drag and reach velocities approaching those of the carrier gas itself. Larger particles, with diameters measured in micrometers and masses millions of times greater, respond more slowly to the same forces and lag behind the expanding gas envelope. This size-dependent acceleration creates the first hints of structure in the comet's dusty envelope. Observations through telescopes equipped with sensitive CCD cameras reveal that the comet's brightness distribution is not perfectly uniform, but shows subtle radial gradients that reflect the different trajectories of particles with different sizes. The innermost regions, closest to the nucleus, contain the full spectrum of dust sizes. Further out, the population becomes progressively dominated by smaller particles as larger grains fall behind in the expansion. The physics governing this process follows well-established principles of aerodynamics and particle dynamics. Yet the extreme conditions near the comet, temperatures hundreds of degrees below terrestrial experience, gas densities a trillion times thinner than Earth's atmosphere, create a regime where intuitive understanding fails and mathematical models become essential. The drag force on a dust grain depends on its cross-sectional area, the density and velocity of the surrounding gas, and a drag coefficient that varies with the ratio of particle size to the mean free path of gas molecules near the nucleus, where gas densities remain relatively high. Collisions between gas molecules and dust grains occur frequently enough to create a regime similar to atmospheric flight. Further from the nucleus, as the gas expands and thins, the mean free path between molecular collisions grows until it exceeds the size of the dust grains themselves. In this free molecular flow regime, each gas molecule that strikes a dust particle transfers its full momentum without the cushioning effect of intermolecular collisions, creating acceleration patterns that differ markedly from those in denser environments. The dust production rate from 3I/8LS increases exponentially as the nucleus warms and more surface area becomes active. Spectroscopic measurements reveal that the comet produces approximately 200 kilograms of dust for every 1,000 kilograms of gas, a dust-to-gas ratio typical of comets but varying significantly with the wavelength of light used for the measurement. This variation occurs because different-sized dust grains scatter light most efficiently at wavelengths comparable to their own dimensions, creating a size-dependent signature that allows astronomers to infer the particle size distribution throughout the coma. Professional observers using large ground-based telescopes begin to detect the first clear evidence of non-radial motion in the dust distribution. High-resolution images processed with sophisticated software to remove the effects of atmospheric turbulence reveal that dust particles do not simply expand outward from the nucleus in straight lines, but follow curved trajectories that reflect the influence of solar radiation pressure. This force, though incredibly weak by terrestrial standards, becomes significant for microscopic particles in the vacuum of space where no atmospheric drag opposes its action. Solar radiation pressure arises from the momentum carried by photons, packets of electromagnetic energy that, despite having no mass, transport momentum according to Einstein's special theory of relativity. When photons strike a dust grain, they transfer their momentum to the particle, creating a force that points radially away from the Sun regardless of the grain's position relative to the comet nucleus. For particles smaller than the wavelength of visible light, this force can exceed the gravitational attraction of both the Sun and the comet, accelerating them to speeds that quickly carry them beyond the gravitational influence of the solar system entirely. The competition between solar radiation pressure and gravitational forces creates a critical particle size, approximately 1 micrometer in diameter, that divides dust grains into two distinct populations. Smaller particles, dominated by radiation pressure, follow trajectories that curve rapidly away from the Sun. Larger particles, dominated by gravitational forces, follow paths that curve more slowly and remain more tightly coupled to the comet's orbital motion. This size segregation becomes increasingly apparent as the dust travels further from the nucleus and solar radiation pressure has more time to act. The observed brightness of dust grains depends not only on their number and size distribution, but also on their composition and structure. Silicate minerals, fragments of olivine, pyroxene, and feldspars that condense from stellar atmospheres, scatter sunlight efficiently at visible wavelengths, organic compounds darkened by eons of cosmic ray bombardment, absorb more light than they reflect, appearing dark against the background of space. Metallic particles, though rare in cometary dust, can produce bright flashes when they rotate and present different faces to illumination. Infrared observations reveal thermal emission from dust grains heated by solar radiation, providing independent measurements of particle temperatures and sizes. The balance between absorbed solar energy and radiated thermal energy determines the equilibrium temperature of each grain, with smaller particles reaching higher temperatures than larger ones due to their higher surface area to volume ratios. These temperature measurements, combined with models of particle heating and cooling, allow astronomers to infer details about grain composition, structure, and even their rotation rates. The expanding dust cloud begins to show the first hints of the asymmetric structure that will eventually develop into a spectacular tale. Careful analysis of brightness distributions in images taken hours apart reveals that dust production is not uniform across the nucleus surface, but varies with longitude as different regions rotate into and out of sunlight. Areas rich in volatile ices produce more gas and, consequently, more dust, or regions dominated by rocky material remain relatively inactive even when heated by solar radiation. This rotational modulation of dust production creates spiral patterns in the coma as the nucleus spins and different active regions contribute their material to the expanding envelope. These structures, invisible to casual observation but clearly revealed in processed images, represent the first departures from simple radial expansion and herald the complex asymmetric phenomena that will soon dominate the comet's appearance. The dust grains themselves carry information about conditions in the interstellar medium where three ice/atlas formed. Isotopic ratios preserved in mineral crystals reflect the nuclear processes that operated in the stellar cores where heavy elements were synthesized. Organic compounds retain chemical signatures of the reducing environment that prevailed in the molecular clouds where ices first condensed around dust cores. Even the size distribution of particles reflects the physics of grain growth and destruction in the tenuous environment between stars. As these ancient messengers begin their dance outward from the nucleus, accelerated by gas drag and shaped by radiation pressure, they carry with them not only the material substance of another stellar system, but also the encoded history of cosmic processes that operated billions of years ago in regions of space now far from our Sun. Their trajectories, measured with exquisite precision by Earth-based observers, will soon reveal patterns of motion that challenge standard theories of comet tail formation and provide new insights into the physics of dust dynamics in the solar wind. The influence of solar radiation pressure begins to assert itself with mathematical precision as 3 ice/atlas crosses the orbital distance where Earth traces its annual path around the Sun. At this distance, the intensity of solar radiation reaches 1,360 watts per square meter, the same flux that powers photosynthesis and drives weather patterns on our home planet. But here, in the vacuum of space, it serves a different purpose. exerting momentum transfer on countless billions of dust grains streaming away from the comet's nucleus in an expanding cloud that now spans several 100,000 kilometers. The momentum carried by each photon of sunlight, though infinitesimally small by everyday standards, becomes significant when multiplied by the immense number of photons striking microscopic particles over periods of weeks and months. Each photon carries momentum equal to its energy divided by the speed of light, a relationship derived from Einstein's special theory of relativity that reveals the fundamental connection between electromagnetic radiation and mechanical force. For a typical dust grain 1 micrometer in diameter, the acceleration produced by solar radiation pressure equals approximately 1 millimeter per second squared, weak compared to terrestrial gravity, but sufficient to dramatically alter particle trajectories over the timescales relevant to comet tail formation. The efficiency with which dust grains absorb and scatter solar radiation depends critically on their size relative to the wavelength of light. Following principles established by Gustav Mie in 1908 through mathematical analysis of electromagnetic scattering by spherical particles, grains much smaller than visible light wavelengths, those with diameters less than 100 nanometers, scatter light according to Rayleigh's law, with efficiency proportional to the fourth power of frequency, explaining why scattered sunlight appears blue just as it does in Earth's atmosphere. Larger grains, with dimensions comparable to or greater than optical wavelengths, follow Mie scattering theory with complex efficiency curves that depend on particle size, composition, and internal structure. This size-dependent interaction with radiation creates a natural sorting mechanism that begins to segregate dust grains according to their physical properties. The smallest particles, those dominated by Rayleigh scattering, experience the strongest radiation pressure relative to their mass and are accelerated most rapidly away from the sun. Intermediate-sized grains experience varying degrees of radiation pressure depending on their precise dimensions and the wavelength-dependent scattering efficiency. The largest particles, those several micrometers in diameter, interact with radiation less efficiently but also possess the greatest inertia, causing them to respond slowly to the constant outward push of solar photons. Professional astronomers studying 3I/Atlas with sophisticated imaging systems begin to detect the subtle but unmistakable signs of this size segregation in the comet's expanding dust envelope. Observations at different wavelengths reveal systematic variations in the comet's brightness distribution that reflect the wavelength-dependent scattering properties of particles with different sizes. Blue light, scattered most efficiently by the smallest grains, shows a brightness distribution that extends further from the nucleus and appears more diffuse than red light, which is scattered primarily by larger particles that remain more tightly concentrated near the comet's center. The development of asymmetry in the dust distribution follows patterns that can be predicted, in principle, from the fundamental physics of particle motion in the solar radiation field. Each dust grain, once liberated from the nucleus by gas drag, follows a trajectory determined by three primary forces: the gravitational attraction of the sun, the outward push of radiation pressure, and any residual influence from the comet's own weak gravitational field. For most particles, the comet's gravity becomes negligible within hours of their release, leaving them subject only to the competing influences of solar gravity and radiation pressure. The ratio of radiation pressure to gravitational force, known as the beta parameter, depends on particle size, density, and optical properties. For typical silicate grains with densities around 2,500 kilograms per cubic meter, particles smaller than approximately 0, 3 micrometers have beta values greater than 1, meaning radiation pressure exceeds solar gravity and accelerates them to velocities that eventually carry them out of the solar system entirely. Larger particles have beta values less than 1 and remain gravitationally bound to the sun, following hyperbolic trajectories that curve away from the comet's path but remain within the solar system's gravitational influence. This fundamental size cutoff creates a natural boundary in the dust population that becomes increasingly apparent as particles travel further from the nucleus and radiation pressure has more time to act. The smallest grains, rapidly accelerated to hyperbolic escape velocities, create a diffuse halo that expands at speeds of tens of kilometers per second. Intermediate-sized particles follow trajectories that curve gradually away from the radial direction, creating the beginnings of a tail structure that points generally away from the Sun, but shows complex curvature reflecting the balance between radiation pressure and orbital motion. The largest dust grains, those approaching 10 micrometers in diameter and containing billions of atoms, respond slowly to radiation pressure and remain more tightly coupled to the comet's orbital motion. These particles form the dense, bright inner regions of the developing tail where dust concentrations remain high enough for significant scattering of sunlight. Their trajectories follow smooth curves that lag behind the comet's motion, creating the characteristic curved shape that gives comet tails their distinctive appearance against the star field. Spectroscopic analysis of sunlight scattered by the dust reveals additional complexity in the particle population. Different mineral compositions produce subtly different scattering spectra, allowing astronomers to identify the presence of olivine, pyroxene, and other silicate minerals in the expanding dust cloud. Organic compounds. Their molecular bonds, modified by eons of cosmic ray bombardment, contribute their own spectral signatures that hint at complex chemistry preserved from the interstellar medium where 3I/Atlas originated. The temperature of dust grains, determined by the balance between absorbed solar energy and radiated thermal emission, provides another diagnostic tool for understanding particle properties. Infrared observations reveal that dust temperatures vary systematically with distance from the nucleus and, surprisingly, with particle size. Smaller grains reach higher equilibrium temperatures than larger ones due to their higher surface area to volume ratios, creating thermal gradients in the dust cloud that can be mapped using sensitive infrared detectors. These temperature measurements reveal unexpected complexity in the dust population, suggesting that particles are not simple spherical grains but possess irregular shapes. Porous structures, or composite compositions that affect their thermal properties. Some dust grains appear to consist of aggregates of smaller particles held together by weak molecular forces, creating fluffy structures with large surface areas that heat efficiently but radiate energy slowly. Others seem to be compact, solid particles that heat slowly but radiate efficiently, reaching different equilibrium temperatures despite experiencing the same solar radiation flux. The emerging picture of 3I/Atlas's dust environment reveals a population of particles that reflects the complex history of its parent nucleus. Grains produced by different active regions on the surface show subtly different properties, suggesting variations in composition. Structure, or formation history across the nucleus. The size distribution of particles varies with time as different regions become active and contribute their material to the expanding cloud, creating temporal variations in the comet's appearance that correlate with the comet's rotational period. As the dust grains continue their outward journey, now clearly segregated by size and following divergent trajectories under the influence of radiation pressure, they begin to trace the graceful curves that will eventually form one of the most spectacular and scientifically significant comet tails ever observed. The stage is set for the development of asymmetric structures that will challenge theoretical understanding and provide new insights into the physics of dust dynamics in the solar system. The asymmetric whispers in 3I/Atlas's tail structure begin to manifest with undeniable clarity as the comet approaches the inner solar system, crossing the orbital distance where Venus traces its scorching path around the Sun. Here, where solar radiation intensity reaches 4 times Earth's orbital value, the subtle irregularities that have been building in the dust and gas distribution finally achieve sufficient contrast to be detected by ground-based telescopes equipped with sensitive imaging systems and sophisticated data processing algorithms. These early asymmetries appear not as dramatic departures from symmetry, but as gentle deviations that require statistical analysis to distinguish from noise and atmospheric turbulence. High-resolution images processed with adaptive optics systems reveal that the brightness distribution in the comet's coma shows systematic variations that cannot be explained by simple radial expansion from a point source. Instead of the expected circular symmetry, the dust and gas envelope displays subtle elongations, brightness gradients, and structural features that hint at complex physical processes operating within the expanding material. The asymmetries manifest differently at different wavelengths of light, revealing the size-dependent nature of the underlying physical mechanisms. Blue light, scattered primarily by submicrometer dust grains, shows brightness variations that extend further from the nucleus and display more pronounced directional structure. Red and infrared wavelengths, dominated by larger particles and thermal emission from heated dust, reveal different patterns of asymmetry that reflect the distinct trajectories followed by particles of different sizes under the influence of radiation pressure and other forces. Spectroscopic observations provide additional evidence for non-uniform conditions throughout the coma. The intensity ratios of emission lines from different molecular species, water, carbon monoxide, carbon dioxide, and various organic compounds vary systematically with position in the gas envelope, indicating that the chemical composition of the escaping material is not uniform. This chemical heterogeneity suggests that different regions of the nucleus surface have different compositions, or that gas phase chemistry is occurring as molecules travel outward through the expanding atmosphere. The rotational modulation of asymmetric features provides crucial clues about their origin. Time-lapse imaging reveals that the structural irregularities in the coma rotate with the same 7-3-hour period as the nucleus, indicating that they originate from non-uniform activity across the comet's surface rather than from external influences or gas phase processes in the coma itself. As the nucleus spins, different active regions contribute their gas and dust to the expanding envelope, creating time-variable patterns that reflect the geography of sublimation on the comet's surface. Detailed photometric analysis reveals that the asymmetries are not random fluctuations, but display coherent structure that persists over multiple rotation periods. Certain regions of the coma consistently appear brighter or dimmer than their surroundings, suggesting the presence of long-lived features that reflect stable characteristics of the nucleus surface or subsurface structure. These persistent asymmetries imply that the comet's activity is controlled not just by solar heating of the immediate surface, but by deeper physical processes that regulate the flow of volatile materials from interior reservoirs to the surface. The mathematical description of these early asymmetries requires sophisticated models that account for the three-dimensional structure of gas and dust flow from multiple active regions on a rotating, irregularly shaped nucleus. Traditional comet models assume spherical symmetry and uniform surface properties, but 3I/Atlas clearly violates these simplifying assumptions. The observed brightness distributions can only be explained by models that incorporate realistic surface topography, non-uniform composition, and the complex interplay between gas dynamics and dust entrainment. Computational fluid dynamics simulations reveal that even modest variations in surface activity can produce significant asymmetries in the expanding coma. Gas jets from localized active regions create pressure gradients that deflect the flow from other areas, leading to complex three-dimensional patterns that evolve as the material expands outward and the comet rotates. The dust component, dragged along by gas flow near the nucleus, but increasingly dominated by radiation pressure at larger distances, follows trajectories that reflect this complex initial velocity field. The thermal physics of the nucleus surface adds another layer of complexity to the asymmetry development. Solar heating penetrates only a few centimeters into the comet's porous structure, creating temperature gradients that drive sublimation primarily from the uppermost layers of ice and dust. However, thermal conductivity within the nucleus allows heat to diffuse laterally and vertically, creating temperature patterns that do not exactly match the instantaneous solar illumination pattern. This thermal lag effect means that maximum sublimation rates may occur hours after peak solar heating, creating phase shifts between illumination and activity that contribute to the observed asymmetries. The composition of escaping gases provides additional evidence for subsurface heterogeneity that contributes to asymmetric tail development. Different volatile compounds sublimate at different temperatures, with carbon monoxide and nitrogen becoming active at much lower temperatures than water ice. As the comet warms during its approach to the Sun, different chemical species become dominant at different times and from different surface regions, creating compositional gradients in the expanding gas that translate into structural features in the developing tail. Infrared spectroscopy reveals unexpected complexity in the organic component of the escaping material. Methanol, formaldehyde, acetylene, and other carbon-bearing molecules show abundance variations that correlate with the brightness asymmetries observed in visible light, suggesting that organic-rich and organic-poor regions on the nucleus contribute differently to the overall mass loss rate. This chemical heterogeneity reflects the complex formation history of the comet in the interstellar medium, where temperature and density variations during accretion created a nucleus with spatially variable composition. The magnetic environment around 3Y/Atlas, though incredibly tenuous compared to planetary magnetospheres, begins to play a subtle role in shaping the asymmetric structures. Solar wind protons and electrons, streaming outward from the Sun at speeds of several hundred kilometers per second, interact with the expanding neutral gas through charge exchange reactions that create a weak but measurable population of ions in the coma. These charged particles respond to magnetic fields embedded in the solar wind, creating asymmetric features that point in directions determined by the interplanetary magnetic field orientation rather than the Sun-comet line. The detection of these first clear asymmetries in 3I/Atlas's coma marks a turning point in the comet's observable evolution. What began as subtle statistical fluctuations in brightness measurements has evolved into unambiguous structural features that violate the spherical symmetry assumed by classical comet models. These early departures from symmetry represent the first manifestations of the complex physical processes that will soon produce one of the most spectacular and scientifically significant asymmetric comet tails ever observed. Ground-based observers begin to coordinate intensive monitoring campaigns, recognizing that 3I/Atlas offers a unique opportunity to study asymmetric tail development in unprecedented detail. The comet's interstellar origin, unusual activity patterns, and favorable viewing geometry combine to create ideal conditions for advancing theoretical understanding of comet physics. The subtle asymmetries now becoming visible represent merely the beginning of a remarkable display that will challenge fundamental assumptions about how comet tails form and evolve. The rotational choreography of 3I/Atlas reveals its secrets with each passing 7.3-hour cycle as ground-based observers maintain continuous surveillance of the comet's evolving coma structure. The nucleus spins with the steady precision of a celestial timepiece, presenting different faces to solar illumination in a rhythm that has remained constant throughout its billion-year journey through interstellar space. Now, as solar heating penetrates the weathered surface layers, this rotation creates systematic variations in sublimation rate that produce the first clear evidence of the comet's non-uniform surface composition and structure. High-cadence photometry reveals that the comet's brightness varies by approximately 0.3 magnitudes, a factor of 1.3 in luminosity, over each rotation period, indicating significant variations in activity level as different regions rotate into and out of direct solar illumination. This rotational light curve displays a complex shape with two unequal maxima and minima per rotation period, suggesting that the nucleus possesses an elongated shape with distinct active regions located at different longitudes on its surface. The asymmetry in the light curve implies that the most active regions are not uniformly distributed around the comet's equator, but are concentrated in specific areas that may reflect the original accretion patterns or subsequent evolutionary processes. Detailed analysis of the rotational variations reveals systematic changes in the relative contributions of different molecular species to the overall gas production rate. Water vapor, the dominant constituent of the escaping gas, shows peak production rates that lag several hours behind maximum solar heating, reflecting the thermal inertia of the nucleus surface layers. Carbon dioxide and carbon monoxide, which sublimate at lower temperatures than water, display different phase relationships with solar illumination, suggesting that these species originate from different depths within the nucleus or from regions with different thermal properties. The dust production rate exhibits even more complex rotational variations than the gas emission, with peak dust release occurring at specific longitudes where surface conditions favor the efficient entrainment of solid particles by expanding gases. Spectrophotometric observations reveal that the color of scattered light from the dust changes systematically with rotational phase, indicating variations in particle size distribution, composition, or structure across the nucleus surface. Some regions produce predominantly small dust grains that scatter blue light efficiently, while others generate larger particles that preferentially scatter red wavelengths. Three-dimensional modeling of the nucleus shape and surface properties, constrained by the observed rotational light curve and brightness distribution, suggests that 3Y/Atlas possesses an elongated structure with an axis ratio of approximately 2.51. The long axis appears to be oriented roughly perpendicular to the spin axis, creating the double-peaked light curve as alternately broad and narrow cross-sections are presented to solar illumination during each rotation. Surface albedo variations of 50% or more are required to explain the amplitude of brightness changes, indicating dramatic differences in composition or structure between active and inactive regions. The active regions responsible for most of the gas and dust production appear to be concentrated in two primary zones located at opposite ends of the nucleus long axis. These areas may represent regions where the original accretion process concentrated volatile-rich materials, or they could be zones where subsequent evolution has removed protective surface layers and exposed subsurface ice deposits. The inactive regions, which produce minimal gas and dust despite receiving similar solar heating, may be covered by a lag deposit of non-volatile dust and rocky debris that insulates underlying ice from direct solar heating. Thermal modeling reveals that the temperature distribution across the nucleus surface shows significant variations that correlate with, but do not exactly match the observed activity patterns. The thermal inertia, a measure of how efficiently the surface conducts and stores heat, appears to vary by factors of 10 or more across the nucleus, with some regions responding rapidly to solar heating, while others maintain nearly constant temperatures throughout the rotation period. This thermal heterogeneity reflects variations in surface porosity, composition, and structure that influence how efficiently solar energy can penetrate into the subsurface ice layers. The subsurface structure of the nucleus, inferred from thermal and gas production models, suggests a complex internal architecture where ice-rich regions alternate with more refractory materials in patterns that may reflect the original conditions during accretion in the interstellar medium. Temperature profiles calculated for different, assumed thermal properties indicate that active sublimation occurs primarily within the uppermost few centimeters of the surface, but lateral heat conduction can extend this active zone several centimeters beyond the directly illuminated areas. Spectroscopic monitoring reveals that the isotopic ratios of different molecular species vary systematically with rotational phase, providing evidence for chemical heterogeneity within the nucleus that reflects its formation in the interstellar environment. The deuterium to hydrogen ratio in water vapor, a sensitive tracer of formation conditions, shows variations that suggest different regions of the nucleus experience different temperatures during the original ice condensation process. These isotopic signatures preserve information about the thermal and chemical conditions that prevailed in the molecular cloud where 3I/Atlas formed billions of years ago. The emerging picture of 3I/Atlas's nucleus reveals a body that is far from the homogeneous, uniformly active object assumed by traditional comet models. Instead, it appears to be a complex assemblage of materials with different compositions, structures, and evolutionary histories, all bound together by weak gravitational forces and perhaps molecular adhesion between dust grains. The rotational variations in activity represent the surface expression of this internal complexity, as different materials respond differently to solar heating and contribute their distinctive signatures to the expanding coma. The implications of this surface heterogeneity for tail development become apparent as the comet continues its inward journey and the activity level increases exponentially with warming. The non-uniform distribution of active regions means that dust and gas production varies not only with heliocentric distance but also with rotational phase, creating time-variable inputs to the tail formation process. This temporal modulation of source strength will prove crucial in understanding the complex asymmetric structures that soon develop in the comet's tail. High-resolution imaging reveals the first hints of discrete jets emanating from specific regions on the nucleus surface, appearing as narrow features in the inner coma that can be traced back to individual active areas. These jets provide direct evidence for localized sublimation from discrete source regions rather than uniform outgassing from the entire surface. The directions of these jets change systematically as the nucleus rotates, confirming that they originate from fixed locations on the surface and are not ephemeral gas phase phenomena. The discovery of jet activity adds another layer of complexity to the developing asymmetric tail structure. Rather than simple radial expansion from the nucleus, the gas and dust flow now includes significant non-radial components that reflect the three-dimensional nature of sublimation from an irregularly active surface. These jet-like flows carry dust grains along trajectories that deviate systematically from the radial direction, creating the seed irregularities that will eventually grow into large-scale asymmetric structures under the influence of solar radiation pressure and solar wind interactions. As 3I/Atlas continues its rotation with clockwork precision, each 3-hour cycle contributes new material to the expanding coma and developing tail, but with systematically varying properties that reflect the complex surface geography of this ancient interstellar wanderer. The rotational revelations provide the key to understanding how internal structural complexity translates into external asymmetric phenomena, setting the stage for the remarkable tail dynamics that will soon unfold. The thermal physics governing 3Y/Atlas's surface creates a complex web of temperature variations that drive asymmetric sublimation patterns with consequences far more profound than the simple heating and cooling cycles might suggest. As the comet orbits closer to the Sun, now within the distance of Mercury's eccentric path, the intensity of solar radiation creates surface temperatures that approach the critical thresholds for rapid water ice sublimation. But the response to this heating occurs not uniformly across the nucleus, but in patterns that reflect the intricate interplay between solar illumination, surface properties, and thermal conduction within the porous cometary material. The phenomenon of thermal lag becomes increasingly significant as heating rates intensify and temperature gradients steepen within the nucleus subsurface layers. Solar energy penetrates only a few centimeters into the comet's structure before being absorbed by dust grains and ice crystals. But this absorbed energy must then diffuse through a complex matrix of solid particles, empty pore spaces, and ice-cemented aggregates with thermal conductivities thousands of times lower than solid rock. The result is a thermal wave that propagates slowly inward during the comet's day and outward during its night, creating subsurface temperature patterns that lag hours behind the surface illumination changes. This thermal inertia effect produces maximum sublimation rates not at local noon when solar heating reaches its peak, but several hours later when heat diffusion finally raises subsurface ice temperatures to their sublimation threshold. The magnitude of this time lag varies dramatically across the nucleus surface depending on local thermal properties, creating a patchwork of peak activity times that contribute to the complex rotational variations observed in gas and dust production. Some regions with high thermal conductivity respond quickly to solar heating, while others with more porous or insulating surface layers show delays of 6 hours or more between peak illumination and maximum activity. The three-dimensional nature of heat conduction within the nucleus creates lateral temperature gradients that drive sublimation in regions not directly illuminated by solar radiation. Heat absorbed in sunlit areas diffuses not only downward into the subsurface, but also sideways into adjacent areas that remain in shadow, raising temperatures in permanently shadowed regions and creating sublimation activity from areas that receive no direct solar heating. This lateral heat transfer can extend active sublimation zones several meters beyond the terminator line that separates day and night on the nucleus surface. Thermal modeling reveals that the nucleus likely possesses a layered structure where surface properties change with depth, creating complex three-dimensional temperature fields that vary not only with time and location, but also with depth below the surface. The uppermost layer, processed by eons of cosmic ray bombardment and modified by previous close approaches to other stars, may have thermal properties significantly different from pristine interior materials. Beneath this weathered rind lies a zone where original ice and dust aggregates remain relatively unmodified, but even deeper layers may have experienced compaction and thermal processing that altered their structure and composition. The porosity of cometary material plays a crucial role in determining thermal response patterns, with typical void fractions ranging from 50% to 90% depending on the degree of compaction and sintering that has occurred during the comet's evolution. High porosity regions act as thermal insulators, preventing efficient heat conduction and creating temperature patterns that respond slowly to changes in solar illumination. Lower porosity areas conduct heat more efficiently, but also store more thermal energy per unit volume, creating different temporal patterns of heating and cooling that contribute to the complex rotational variations in activity. Sublimation-driven cooling provides a negative feedback mechanism that regulates surface temperatures and prevents runaway heating even under intense solar illumination. As ice sublimes, it absorbs approximately 2,800 joules per gram of latent heat energy, cooling the immediate surroundings and reducing the temperature gradient that drives further sublimation. This thermostat effect means that actively subliming regions rarely exceed temperatures much above the ice sublimation point, regardless of the intensity of solar heating. While inactive regions with no available ice can reach much higher temperatures, the competition between solar heating and sublimative cooling creates distinct thermal regimes across the nucleus surface that correlate strongly with surface composition and structure. Ice-rich regions maintain relatively constant temperatures near the sublimation point as long as ice remains available, while ice-poor areas experience large temperature swings that follow the solar illumination pattern more closely. These thermal differences translate directly into variations in sublimation rate and dust production efficiency, contributing to the observed heterogeneity in coma structure and brightness. Infrared observations reveal systematic temperature variations across the visible portions of the nucleus surface that provide direct evidence for the complex thermal processes operating within the cometary material. The warmest regions correspond not necessarily to areas receiving the most direct solar illumination, but to locations where thermal properties favor efficient heat retention and slow sublimative cooling. Conversely, the coolest areas often coincide with regions of intense sublimation activity where evaporative cooling dominates the thermal balance. The thermal skin depth, the distance over which temperature variations propagate into the subsurface, depends on both the thermal diffusivity of the material and the time scale of temperature variations. For daily thermal cycles driven by nucleus rotation, this skin depth typically extends only 1–2 centimeters into the surface, but for longer-term variations associated with orbital motion, thermal effects can penetrate tens of centimeters deep. This depth dependence means that ice reservoirs at different levels within the nucleus become active at different times during the comet's approach to the Sun. Thermophysical modeling suggests that 3I/Atlas's nucleus contains multiple ice reservoirs with different activation temperatures and thermal responses, creating a temporal sequence of activity onset as the comet warms. The most volatile components, carbon monoxide and nitrogen ices, began subliming in the outer solar system, while water ice became dominant only as temperatures rose above approximately -140 degrees Celsius. Even higher temperatures may be required to activate deeply buried ice deposits protected by overlying layers of dust and rocky debris. The asymmetric thermal response of different surface regions creates systematic imbalances in gas production that, when combined with the nucleus rotation, generate spiral patterns in the expanding coma that serve as the foundation for the complex tail structures that will soon develop. Areas that experience peak heating during one part of the rotation period contribute material to specific sectors of the coma, while regions active during other rotational phases add their contributions to different angular sectors. This rotational modulation of thermal activity creates the time-variable source conditions that are essential for understanding the remarkable asymmetric phenomena that distinguish 3I/Atlas from more typical comets. The thermal lag phenomenon also creates systematic differences between the day and night sides of the comet that persist for hours after the terminator passes, contributing to asymmetric mass loss patterns that influence the development of non-gravitational forces. These forces, though tiny compared to solar gravity, can accumulate over time to produce measurable changes in orbital motion that provide additional constraints on models of surface thermal processes and mass loss rates. The segregation of dust particles by size begins to manifest as a visible phenomenon in 3I/Atlas's expanding coma as radiation pressure acts with increasing effectiveness on the microscopic grains streaming away from the nucleus in ever-growing numbers. The physical process underlying this segregation follows from fundamental principles of electromagnetic momentum transfer, but its observable consequences create patterns of startling beauty and complexity that transform the comet's appearance from a simple fuzzy star into a structured, asymmetric object displaying clear evidence of the size-dependent forces acting on its dust population. Particles released from the nucleus begin their journey with velocities determined primarily by gas drag from expanding water vapor and other subliming species. But as they travel outward and the gas density decreases exponentially with distance, radiation pressure from solar photons becomes the dominant force shaping their trajectories. The magnitude of this radiation pressure depends critically on particle size through the complex physics of electromagnetic scattering, creating systematic differences in acceleration that sort the dust population according to physical dimensions with the precision of a cosmic sieve. The smallest dust grains, those with diameters measured in tens of nanometers and containing only thousands of individual atoms, experience radiation pressure forces that exceed solar gravity by factors of 10 or more. These tiny particles accelerate rapidly outward at speeds approaching several kilometers per second, quickly escaping not only the comet's gravitational influence, but eventually the solar system itself. Their trajectories follow nearly straight lines pointing radially away from the Sun, creating a diffuse halo of submicrometer dust that expands at hyperbolic velocities and disperses into interplanetary space within weeks of its release from the nucleus. Intermediate-sized particles, with diameters ranging from 100 nanometers to several micrometers, experience radiation pressure comparable to or slightly exceeding solar gravity. Following curved trajectories that sweep gracefully away from the comet's orbital path, the exact curvature of these trajectories depends on the precise balance between radiation pressure and gravitational forces, which in turn depends on particle density, composition, and optical properties as well as size. Silicate grains follow different paths than organic particles of the same size due to differences in their interaction with solar radiation. The largest dust grains in the population, those approaching 10 micrometers in diameter and containing billions of atoms, respond slowly to radiation pressure because their mass increases as the cube of their diameter, while their cross-sectional area for intercepting photons increases only as the square. These massive particles remain more tightly coupled to the comet's orbital motion, following trajectories that curve gradually away from the radial direction but maintain velocities close to the comet's own orbital speed. They form the backbone of the visible tail structure, providing the high particle densities required for efficient scattering of sunlight back toward Earth-based observers. This natural size segregation creates distinct zones within the developing tail structure that can be distinguished by their optical properties, particle velocities, and temporal evolution. The inner regions, dominated by large particles moving slowly under weak radiation pressure, appear bright and well-defined against the background stars. The middle zones, populated by intermediate-sized grains following moderately curved trajectories, show more diffuse brightness distributions with systematic curvature that reflects the balance between radiation and gravitational forces. The outer regions, containing the fastest-moving, smallest particles, appear as a faint, extended halo that fades gradually into the background. Observations at different wavelengths reveal the wavelength-dependent nature of the size segregation process with striking clarity. Blue light, scattered most efficiently by particles comparable to or smaller than its 450 nanometer wavelength, highlights the distribution of submicrometer grains that have been accelerated to high velocities by strong radiation pressure. Red light, scattered primarily by larger particles, traces the distribution of micrometer-sized grains that follow more tightly curved trajectories under weaker radiation pressure. Infrared observations reveal thermal emission from the largest particles, which retain heat most efficiently due to their favorable surface area to volume ratios. The temporal evolution of size segregation can be traced through time-lapse imaging that reveals how particles of different sizes spread out along divergent trajectories as they travel away from the nucleus. Initially, all particle sizes remain mixed together in the dense inner coma where gas drag dominates over radiation pressure. But as the expanding material travels outward and radiation pressure has more time to act, clear separation develops between fast-moving small particles and slow-moving large ones, creating the characteristic curved, stratified structure of a well-developed comet tail. Spectrophotometric analysis reveals that the color of scattered light changes systematically with position in the tail, providing direct evidence for the size segregation process. Regions dominated by small particles appear relatively blue, while areas with higher concentrations of large particles appear redder. The transition between these color regimes traces the boundary between different size populations and provides quantitative information about the particle size distribution and its evolution with time and distance from the nucleus. The efficiency of size segregation depends on several factors beyond simple particle diameter, including grain density, porosity, and internal structure. Fluffy aggregate particles with low bulk densities experience stronger radiation pressure than compact grains of the same size, leading to more complex segregation patterns that reflect the structural diversity of dust grains produced by different sublimation processes. Some particles appear to be loose aggregates of smaller components that may disaggregate under the influence of solar heating or mechanical stress, creating populations of secondary particles with properties different from the original grains. Polarimetric observations provide additional insights into particle properties and size distributions through measurements of how dust grains scatter polarized light. The degree and direction of polarization depend on particle size, shape, and composition in ways that can be modeled theoretically and compared with observations to infer physical properties. Small particles produce higher degrees of polarization than large ones, while irregular shapes create different polarization signatures than spherical grains. The magnetic properties of dust grains, though typically weak, can be detected through their influence on polarized light scattering and provide information about the presence of metallic iron and other magnetic minerals in the particle population. Some grains appear to contain nanoscale iron inclusions that affect their optical properties and may influence their response to magnetic fields embedded in the solar wind, creating additional complexity in particle trajectories beyond the effects of size-dependent radiation pressure. The size segregation process creates favorable conditions for the development of asymmetric tail structures because different particle size populations respond differently to perturbations and non-uniformities in the gas flow from the nucleus. Small particles, already moving at high velocities under strong radiation pressure, amplify any initial directional variations in their release from the surface. Large particles, moving slowly and remaining more tightly coupled to the gas flow, preserve information about the three-dimensional structure of sublimation patterns on the nucleus for longer periods as they travel outward. As the dust size segregation becomes increasingly apparent in telescopic observations of 3I/8LAS, it provides the physical foundation for understanding how initial asymmetries in gas and dust production at the nucleus translate into large-scale structural features in the tail. The systematic separation of particles by size creates natural boundaries and interfaces within the tail where different physical processes dominate, setting the stage for the development of the complex asymmetric phenomena that will soon transform this interstellar visitor into one of the most scientifically significant comets ever observed. The solar wind's embedded magnetic field begins to exert its subtle but measurable influence on the charged particle population within 3Y/8LAS, Y is expanding coma as the comet approaches the inner solar system, where the density and magnetic field strength of the streaming solar plasma reach values sufficient to affect the motion of ions created by photoionization and charge exchange processes. This interaction between the solar wind and cometary material represents one of the most complex and poorly understood aspects of comet physics, involving the coupling between neutral gas dynamics, plasma physics, and magnetohydrodynamic processes in a regime where traditional approximations often fail and numerical simulations struggle to capture the full range of relevant physical scales. The solar wind itself carries the signature of magnetic fields rooted in the sun's corona and stretched into spiral patterns by the star's rotation and the outward flow of charged particles. This interplanetary magnetic field, though incredibly weak by terrestrial standards, with typical strengths of only a few nanotesla, becomes dynamically important in the tenuous plasma environment surrounding active comets where magnetic pressure can compete with gas pressure in determining the structure and evolution of the ionized component of the coma. Within 3I/Atlas's neutral coma, ultraviolet photons from the sun create a sparse population of ions and electrons through photoionization of water, carbon dioxide, and other molecular species. The rate of ion production increases quadratically with gas density near the nucleus where collisional processes dominate, but decreases with the inverse square of heliocentric distance as solar ultraviolet flux diminishes. Additionally, charge exchange reactions between solar wind protons and neutral cometry molecules create a secondary ion population with different velocity and spatial distributions than the photoions produced by solar radiation. These newly created ions, born with the same velocities as their neutral parent molecules, find themselves immersed in the rapidly flowing solar wind plasma moving at speeds of 400, 800 kilometers per second. The resulting velocity difference creates strong electric fields that accelerate the cometry ions and deflect the solar wind protons, establishing a complex interaction region where momentum and energy transfer occurs between the two plasma populations. The embedded magnetic field plays a crucial role in this process by constraining the motion of charged particles and determining the spatial structure of the acceleration regions. The asymmetric nature of magnetic field interactions becomes apparent through several physical mechanisms that operate on different spatial and temporal scales. The orientation of the interplanetary magnetic field varies continuously as the solar wind carries different field line configurations past the comet, creating time-variable asymmetries in ion acceleration patterns and plasma flow directions. When the magnetic field lies primarily in the plane perpendicular to the Sun-Comet line, the resulting ion trajectories create symmetric patterns around the comet. However, when significant field components point toward or away from the Sun, the symmetry breaks, and ions are preferentially accelerated in directions determined by the magnetic field geometry rather than the radial solar direction. High-resolution spectroscopic observations reveal the presence of ionic species in 3 Y/Atlas's coma through their characteristic emission lines in the ultraviolet and visible portions of the electromagnetic spectrum. Water group ions, primarily H2O+ and OH+, produce emission features that can be mapped spatially to reveal the three-dimensional distribution of ionized material throughout the coma. These observations show systematic asymmetries in ion density and velocity that correlate with variations in the interplanetary magnetic field direction measured by spacecraft throughout the solar system. The plasma tail that develops from the interaction between solar wind and cometry ions displays fundamentally different physics than the dust tail formed by radiation pressure on solid particles. While dust grains follow predictable ballistic trajectories determined by their size and the ratio of radiation pressure to gravitational force, ions respond collectively through electromagnetic forces that depend on the global structure of magnetic fields and electric currents throughout the interaction region. The result is a plasma tail that can change direction rapidly as solar wind conditions vary, sometimes appearing to disconnect entirely from the comet and regenerate in a different direction. Magnetohydrodynamic instabilities develop at the boundaries between different plasma regions within the cometry environment, creating complex time-variable structures that contribute to the asymmetric appearance of the plasma tail. These instabilities arise from velocity shears between the solar wind and cometry plasma, magnetic field discontinuities, and pressure gradients that develop as the expanding neutral coma interacts with the flowing solar wind. The growth rates and spatial patterns of these instabilities depend on local plasma parameters and magnetic field configurations in ways that are difficult to predict without detailed numerical simulations. The magnetic field strength within the cometry plasma environment shows significant enhancements over the typical interplanetary values due to the pileup of magnetic flux as the solar wind encounters the obstacle presented by the expanding neutral coma. This magnetic field compression occurs because magnetic field lines cannot easily penetrate regions of high electrical conductivity, causing them to drape around the ionized portions of the coma and create regions of enhanced field strength that can exceed the background interplanetary values by factors of 10 or more. Particle acceleration processes within the cometry plasma environment create populations of energetic ions and electrons that can be detected through their electromagnetic emissions and their influence on the optical properties of the surrounding gas, some ions are accelerated to speeds comparable to the solar wind velocity through pickup processes that occur when newly ionized particles encounter the magnetic field carried by the solar wind. Others achieve even higher energies through magnetic reconnection events and shock acceleration mechanisms that operate at plasma boundaries and current sheets within the interaction region. The asymmetric distribution of magnetic field strength and direction creates preferential paths for energetic particle propagation that contribute to the overall asymmetry of the tail structure. Particles following magnetic field lines can travel large distances without significant energy loss, creating extended features in the tail that reflect the three-dimensional geometry of the magnetic field rather than simple radial expansion from the nucleus. These field-aligned structures can persist for days or weeks as they are carried outward by the solar wind, creating observable asymmetries that evolve slowly compared to the rapid changes in local plasma conditions. The interaction between magnetic fields and the neutral gas component of the coma occurs primarily through ion-neutral coupling processes that transfer momentum and energy between charged and uncharged particles through collisions and electromagnetic forces. In regions where the ion density remains high enough for frequent collisions with neutral molecules, the magnetic field can indirectly influence neutral gas flow patterns by controlling ion motion and creating pressure gradients that affect the overall gas dynamics. This coupling becomes particularly important near the nucleus, where gas densities are highest and ion-neutral collision frequencies can exceed the ion cyclotron frequency. Observational signatures of magnetic field effects in 3I/Atlas include systematic asymmetries in spectral line intensities, variations in plasma tail morphology that correlate with solar wind magnetic field measurements, and temporal variations in ion emission that reflect the passage of different magnetic field configurations past the comet. These signatures provide crucial constraints on theoretical models of comet-solar wind interaction and offer insights into plasma physics processes that operate throughout the solar system and beyond. As 3I/Atlas continues its approach toward perihelion, the increasing density of both neutral and ionized material in its coma creates conditions where magnetic field effects become increasingly important in determining the overall structure and evolution of both the plasma and dust components of the tail. The complex interplay between neutral gas dynamics, radiation pressure on dust, and electromagnetic forces on ionized particles creates a rich phenomenology that challenges theoretical understanding and provides opportunities for advancing knowledge of fundamental plasma physics processes. The formation of discrete jets emanating from specific regions of 3Y/Atlas's nucleus represents a dramatic departure from the idealized spherical outgassing assumed by classical comet models, creating localized streams of gas and dust that break the radial symmetry of coma expansion and establish the foundation for the complex asymmetric tail structures that will soon dominate the comet's appearance. These jets manifest as narrow, well-defined features in high-resolution images of the inner coma, appearing as bright streaks or plumes that can be traced from their origins near the nucleus surface outward for tens of thousands of kilometers before they merge with the more diffuse background of the general coma expansion. The physical mechanisms responsible for jet formation involve the interplay between subsurface ice sublimation, gas pressure buildup, and the structural properties of the nucleus, surface layers that control how and where escaping gas can reach space. Unlike uniform sublimation from an exposed ice surface, jet formation requires conditions where gas production occurs beneath some form of surface crust or debris layer that restricts outflow to specific outlet points. As sublimation proceeds in subsurface cavities or along fracture networks, gas pressure builds until it exceeds the mechanical strength of the overlying material, creating focused outflow through weak points, cracks, or pre-existing vents in the surface structure. The thermodynamics of subsurface gas production create conditions favorable for jet formation when solar heating penetrates through porous surface layers and reaches ice deposits at depths of several centimeters to meters below the immediate surface. At these depths, sublimation can proceed rapidly once temperatures rise above the critical threshold, but the escaping gas must travel through tortuous pathways within the porous nucleus structure before reaching space. This subsurface transport creates pressure gradients that focus the flow toward regions where the overlying material offers the least resistance to gas escape. Observational evidence for discrete jet activity in 3I/Atlas comes from multiple independent techniques that reveal both the spatial structure and temporal behavior of these localized outflow regions. Direct imaging with high-resolution telescopes shows narrow, linear features in the inner coma that maintain consistent orientations over periods of hours, indicating that they originate from fixed locations on the rotating nucleus surface. Time-lapse photography reveals that these features rotate with the same period as the nucleus, confirming their connection to specific geographic locations rather than transient gas phase phenomena in the expanding coma. Spectroscopic mapping of the jet regions reveals enhanced concentrations of specific molecular species that provide clues about the subsurface chemistry and physical conditions where the jets originate. Water vapor dominates most jets, but some show enhanced abundances of carbon dioxide, carbon monoxide, or organic molecules that suggest variations in subsurface composition or temperature conditions between different jet source regions. The velocity dispersion of molecules within individual jets exceeds that expected for simple thermal motion, indicating that gas acceleration processes within the subsurface flow channels contribute additional kinetic energy to the escaping material. The dust entrainment efficiency varies significantly between different jets, with some producing dust-to-gas ratios 10 times higher than the global average, while others remain virtually dust-free despite strong gas production. This variation reflects differences in the mechanical properties of surface materials overlying different jet source regions, with some areas containing easily eroded dust deposits that can be efficiently entrained by gas flow, while others consist of more consolidated material that resists particle mobilization. The size distribution of dust particles also varies between jets, suggesting that different entrainment mechanisms operate in regions with different structural properties. Three-dimensional modeling of jet trajectories requires sophisticated computational fluid dynamics that account for the transition from subsurface flow through porous media to free expansion in the vacuum of space. Near the surface outlets, gas flow remains in the hydrodynamic regime where intermolecular collisions determine the bulk motion of the expanding material. At distances of hundreds of meters to kilometers from the nucleus, the gas density decreases sufficiently that molecular collisions become rare and individual particles follow ballistic trajectories under the influence of radiation pressure and gravitational forces. The collimation properties of different jets provide information about the geometry and size of their subsurface source regions and surface outlets. Highly collimated jets that maintain narrow widths over large distances suggest outflow through small, well-defined vents, while more divergent plumes indicate broader source regions or multiple closely spaced outlets. The opening angles of jet expansion follow patterns predicted by gas dynamic theory for flow through nozzles and orifices, allowing estimates of source region dimensions and gas production rates from photometric measurements of jet brightness and structure. The temporal behavior of jet activity shows complex patterns that reflect the interplay between solar heating cycles, thermal diffusion within the nucleus, and the mechanical response of surface materials to pressure variations. Some jets display activity that closely follows the solar illumination pattern of their source regions, turning on shortly after sunrise and reaching peak intensity several hours later as thermal diffusion raises subsurface temperatures above the sublimation threshold. Other jets show delayed or irregular activity patterns that suggest more complex subsurface thermal processes or mechanical effects related to pressure buildup and release. Jet variability on timescales shorter than the nucleus rotation period indicates that some jets are intrinsically unstable, possibly due to mechanical failure of surface materials under gas pressure or changes in subsurface flow patterns as ice sublimates and alters the permeability of porous pathways. Rapid jet brightening events lasting minutes to hours have been observed in several instances, suggesting sudden increases in gas production rate or changes in dust entrainment efficiency that may result from the collapse or opening of subsurface cavities. The three-dimensional orientation of jets relative to the nucleus rotation axis and surface topography provides constraints on the internal structure and mechanical properties of the nucleus material. Most jets appear to originate from slopes facing toward the Sun, consistent with solar heating as the primary driver of sublimation. But some jets emanate from regions that should receive minimal direct solar heating, suggesting that lateral heat conduction or other energy sources contribute to their activity. The preferential orientation of jet directions may also reflect the influence of structural weaknesses in the nucleus material that control where gas pressure can most easily create surface outlets. The interaction between multiple jets operating simultaneously creates complex interference patterns in the inner coma where their individual plumes overlap and merge. High-resolution imaging reveals spiral structures and braided patterns that result from the superposition of jets with different source locations, orientations, and activity levels as the nucleus rotates and presents different combinations of active regions to solar heating. These interference effects contribute significantly to the overall asymmetry of the coma structure and provide the initial conditions for the large-scale tail asymmetries that develop as the material travels outward under radiation pressure. Dust dynamics within jets differ significantly from the general coma expansion due to the higher gas velocities and more focused flow patterns that characterize jet environments. Particles entrained in jet flows achieve higher initial velocities than those released by general surface sublimation, leading to systematic differences in their subsequent trajectories under radiation pressure. Large particles that might otherwise remain gravitationally bound to the comet can achieve escape velocities when accelerated by energetic jet flows, contributing to enhanced dust production from active jet regions. The chemical composition of jet material provides insights into the subsurface reservoirs from which they draw their gas and dust components. Isotopic ratios measured in jet emissions show variations that suggest different jets tap into subsurface regions with different formation histories or evolutionary experiences. Some jets show enhanced deuterium abundance in water vapor, indicating access to primitive ice deposits that preserve the isotopic signature of the interstellar medium where the comet formed, while others display isotopic ratios more similar to typical solar system values. As 3I/Atlas continues its inward journey and jet activity intensifies with increasing solar heating. These discrete outflow regions become increasingly important in determining the overall structure and evolution of the comet's asymmetric tail. The non-radial velocity components imparted to gas and dust by jet acceleration create systematic deviations from simple radial expansion that seed the development of large-scale asymmetric structures as the material travels outward and experiences the full effects of radiation pressure and solar wind interactions. The gravitational influence of Jupiter, though separated from 3I/Atlas by hundreds of millions of kilometers, begins to exert measurable perturbations on the trajectories of dust particles streaming away from the comet as they travel outward through the solar system's complex gravitational landscape. This distant influence, barely perceptible compared to the dominant forces of solar gravity and radiation pressure, nonetheless creates systematic deflections in particle paths that accumulate over weeks and months to produce observable asymmetries in the tail structure that reflect the three-dimensional architecture of planetary gravitational fields extending far beyond their immediate orbital neighborhoods. The mathematics of gravitational perturbations in the three-body problem involving the Sun, Jupiter, and individual dust grains requires sophisticated numerical integration techniques that account for the time-varying relative positions of all massive bodies as they follow their respective orbital motions. Each dust particle, once released from the comet nucleus, follows a trajectory determined by the vector sum of gravitational forces from all solar system bodies. But the computational complexity of tracking millions of particles simultaneously through this multi-body gravitational field challenges even modern supercomputers and requires careful approximation methods to achieve tractable solutions. Jupiter's gravitational field extends throughout the solar system with a strength that decreases as the inverse square of distance, but its influence on dust particle trajectories depends not only on field strength, but also on the relative velocities and orbital geometries that determine how long particles remain within regions where Jovian gravity can significantly alter their motion. Particles traveling on trajectories that pass near Jupiter's orbital zone experience stronger and longer duration perturbations than those following paths that remain in the inner solar system, creating systematic differences in deflection angles that translate into observable structural features in the comet's tail. The perturbative effects of planetary gravity on dust trajectories become most apparent for intermediate-sized particles with diameters ranging from 1 to 10 micrometers, which experience radiation pressure forces comparable to but not vastly exceeding solar gravity. These particles follow curved trajectories under radiation pressure that can be significantly modified by additional gravitational influences from massive planets, particularly when their paths carry them through regions of space where planetary gravity fields achieve their maximum effectiveness relative to competing forces. Smaller particles, those dominated by strong radiation pressure that accelerates them to hyperbolic escape velocities, spend too little time within the solar system for planetary perturbations to accumulate significant effects on their trajectories. Conversely, the largest particles, those that remain gravitationally bound to the Sun and follow nearly Keplerian orbits, experience planetary perturbations similar to those affecting asteroids and other small solar system bodies. But these particles contribute less significantly to the observable brightness of the comet's tail due to their lower number densities and reduced light scattering efficiency. The temporal evolution of gravitational perturbations depends critically on the orbital positions of perturbing planets at the time when dust particles pass through their zones of influence. Jupiter's 12-year orbital period means that its position relative to the comet's trajectory changes significantly between successive passages of similar particles, creating time-variable perturbation patterns that contribute to the complex temporal evolution of tail asymmetries. Particles released from the nucleus weeks or months apart experience different planetary configurations and consequently follow systematically different perturbed trajectories. Observational evidence for gravitational perturbations appears in the form of systematic curvatures and deflections in the tail structure that cannot be explained by radiation pressure alone. High-resolution imaging reveals subtle but measurable deviations from the smooth, curved trajectories predicted by models that include only solar gravity and radiation pressure, with particles appearing to follow slightly different paths depending on when they were released from the nucleus and what planetary configurations they encountered during their outward journey. The three-dimensional nature of gravitational perturbations creates effects that are most apparent when viewed from Earth's changing perspective as our planet orbits the Sun. The apparent position angle of the comet's tail axis shifts slightly over periods of weeks to months in ways that reflect the combined influences of changing viewing geometry and the gravitational deflection of tail material by planetary bodies. These subtle geometric effects require careful analysis to separate from other sources of tail asymmetry, but they provide unique information about the three-dimensional structure of particle trajectories throughout the tail. Numerical simulations of dust dynamics that include gravitational perturbations from all major planets reveal complex interference patterns where the influences of different planetary bodies alternately reinforce and cancel each other depending on orbital configurations and particle properties. When Jupiter and Saturn are aligned on the same side of the solar system, their combined gravitational influence can create more pronounced deflections than when they are positioned on opposite sides and their effects partially cancel. These planetary configuration effects contribute to long-term variations in tail morphology that correlate with the orbital periods of the giant planets. The gravitational focusing effect, whereby planetary masses can concentrate particles along specific trajectories through their gravitational influence, creates regions of enhanced particle density within the tail that appear as brightness enhancements or structural features in high-resolution images. This effect is most pronounced for particles whose initial velocities and directions are precisely matched to the gravitational assistance provided by planetary encounters, creating preferential trajectories that collect more particles than surrounding regions. Resonance effects between particle orbital periods and planetary orbital periods can trap certain populations of dust grains in long-lived orbital configurations that keep them within the inner solar system for extended periods rather than allowing them to escape to interstellar space. These trapped particles contribute to the zodiacal dust complex that pervades the solar system and can create persistent features in the comet's tail that evolve slowly compared to the rapidly dispersing material that escapes planetary influence quickly. The influence of smaller planets and large asteroids, though individually negligible compared to Jupiter's effects, can create cumulative perturbations when particles pass through regions of space where multiple small bodies contribute their gravitational influences simultaneously. The asteroid belt, in particular, represents a region where the combined gravitational effects of thousands of rocky bodies can produce measurable deflections in dust particle trajectories, particularly for particles that travel slowly enough to spend significant time within this gravitationally complex environment. Mars, despite its small mass compared to Jupiter, can produce observable effects on dust trajectories when 3I/8 orbital geometry brings the comet's tail material close to the red planet's orbital zone. The timing of such encounters depends on the specific orbital elements of the comet and the positions of Mars at the relevant times, creating opportunities for detailed observational studies of gravitational perturbation effects under well-controlled conditions where other variables can be constrained. The Earth-Moon system presents a unique opportunity for studying gravitational perturbations because ground-based observers can directly measure the positions and motions of dust particles as they pass through the Earth's gravitational influence zone. Precise astrometric measurements of particle positions relative to background stars can reveal the subtle deflections caused by terrestrial gravity, providing direct observational confirmation of perturbation theories and validation of computational models used to predict particle trajectories throughout the solar system. As 3I/Atlas continues its journey through the solar system's gravitational landscape, the accumulating effects of planetary perturbations contribute increasingly complex asymmetric features to its tail structure. These gravitationally induced asymmetries add another layer of complexity to the already intricate patterns created by size-dependent radiation pressure, magnetic field interactions, and the non-uniform source conditions at the nucleus, creating a tail structure of unprecedented complexity that challenges theoretical understanding and provides new insights into the dynamics of small particles in planetary gravitational fields. The chemical differentiation of volatile compounds within 3I/Atlas's expanding coma creates a complex tapestry of molecular species that sublimate at different rates and temperatures, establishing compositional gradients throughout the tail that reflect both the heterogeneous nature of the nucleus and the temperature-dependent physics of phase transitions in the extreme environment of interplanetary space. This chemical diversity, far exceeding the simple water-dominated composition assumed by early comet models, reveals the remarkable molecular complexity preserved within interstellar ice deposits and provides insights into the chemical processes that operated during the comet's formation in the molecular clouds surrounding distant stellar systems. Water ice, though constituting the major fraction of volatile material in most comets, begins significant sublimation only when surface temperatures rise above approximately -140 degrees Celsius, a threshold that 3Y/Atlas crossed during its approach through the outer solar system. However, the comet's chemical inventory extends far beyond water to include carbon dioxide, carbon monoxide, methanol, formaldehyde, acetylene, hydrogen cyanide, and dozens of other molecular species that each possess their own characteristic sublimation temperatures, vapor pressures, and chemical stability properties that determine when and where they contribute to the expanding gas envelope. Carbon dioxide ice, with a sublimation temperature of -78 degrees Celsius at standard pressure, begins outgassing at much greater heliocentric distances than water, creating an extended envelope of CO2 molecules that surrounds the inner water-dominated coma throughout the comet's approach to the Sun. This early CO2 activity produces subtle brightness enhancements that can be detected spectroscopically long before visual observers notice any significant coma development, providing advance warning of the comet's awakening and establishing the chemical foundation for the complex tail structures that will eventually develop. The more exotic volatile compounds present in trace quantities within the nucleus create distinctive spectral signatures that appear and disappear as local temperatures and chemical conditions change throughout the expanding coma. Methanol, with its relatively low sublimation temperature and high chemical reactivity, produces characteristic emission lines in the infrared portion of the spectrum that vary in intensity with both heliocentric distance and rotational phase, as different regions of the nucleus surface contribute their chemical inventories to the expanding gas envelope. The spatial distribution of different molecular species within the coma reflects not only their sublimation properties, but also their chemical reactivity and photodissociation rates under intense solar ultraviolet radiation. Water molecules, once released from the nucleus, remain stable for hours to days before being dissociated by ultraviolet photons into hydroxyl radicals and hydrogen atoms. Carbon dioxide molecules show greater stability against photodissociation, but can undergo chemical reactions with other species to produce carbon monoxide and atomic oxygen. These photochemical processes create secondary molecular populations with different spatial and velocity distributions than the primary species released directly from the nucleus. The isotopic composition of different molecular species provides additional information about the formation conditions and evolutionary history of the nucleus material. Heavy water, containing deuterium instead of ordinary hydrogen, shows abundance patterns that reflect the temperature and radiation environment during the original ice condensation process in the interstellar medium. Carbon monoxide with different isotopic ratios of carbon and oxygen isotopes preserves signatures of stellar nucleosynthesis processes that operated in the parent molecular cloud where the comet's building materials first condensed around dust grains. Gas chromatography techniques applied to spectroscopic observations reveal the presence of complex organic compounds that form through chemical reactions between simpler molecules during the sublimation and expansion process. Formaldehyde, acetaldehyde, and other small organic molecules can combine under the influence of solar radiation and cosmic ray bombardment to produce larger organic species that may include amino acids, purines, and other biologically relevant compounds. These chemical synthesis processes occur throughout the coma as molecules travel outward and experience changing temperature, density, and radiation conditions. The temperature dependence of chemical equilibrium processes within the expanding gas creates systematic variations in molecular abundance ratios that change with distance from the nucleus and local thermal conditions. Reactions that favor the formation of complex molecules at low temperatures may reverse at higher temperatures closer to the nucleus, while other reactions that require thermal activation energy may only proceed in the warmer inner regions of the coma. These temperature-dependent chemical processes contribute to the observed gradients in molecular abundances throughout the tail structure. The interaction between different molecular species and solar radiation creates wavelength-dependent photodissociation and ionization processes that establish complex chemical networks throughout the coma. Ultraviolet photons with energies exceeding the ionization potentials of various molecules create ion-electron pairs that participate in a rich chemistry of charge transfer reactions, electron-ion recombination processes, and ion-molecule reactions that can produce molecular species not present in the original nucleus material. Observational techniques for studying chemical differentiation include high-resolution spectroscopy at ultraviolet, visible, infrared, and radio wavelengths that can identify and map the spatial distribution of dozens of different molecular species throughout the coma and tail. Each molecular species produces characteristic emission or absorption lines at specific wavelengths that serve as fingerprints for identification and abundance determination. The relative intensities of different spectral lines provide information about excitation conditions, molecular abundances, and chemical reaction rates throughout the expanding gas envelope. The temporal evolution of chemical composition reflects the changing thermal and radiation environment as the comet approaches the Sun, and different volatile reservoirs within the nucleus become active. Early in the approach, when temperatures remain low, the most volatile species dominate the chemical inventory. As heating intensifies, water ice begins to contribute significantly. And at the highest temperatures near perihelion, even refractory organic compounds may begin to sublimate and contribute their molecular signatures to the observed spectra. Chemical modeling of the coma environment requires sophisticated thermochemical calculations that account for the coupled effects of gas dynamics, radiation transport, chemical kinetics, and energy transfer processes. The low density and high temperature gradients characteristic of cometary comae create conditions far from chemical equilibrium, where reaction rates depend critically on local physical conditions and the availability of specific catalytic processes that may accelerate or inhibit particular chemical pathways. The preservation of interstellar chemical signatures within the nucleus material provides unique opportunities for studying the chemistry of star-forming regions and molecular clouds that existed billions of years ago in distant parts of the galaxy. Isotopic ratios, molecular abundance patterns, and chemical complexity preserved in cometary ices represent archived samples of interstellar chemistry that can be analyzed in detail as the comet approaches the Sun and releases its ancient molecular inventory into space. As 3I/Atlas continues its chemical evolution during its passage through the inner solar system, the complex interplay between sublimation, photochemistry, and gas dynamics creates an increasingly diverse molecular environment that contributes multiple chemical traces to the developing tail structure. Different molecular species follow slightly different trajectories under the influence of radiation pressure and magnetic field interactions, creating chemical gradients and compositional asymmetries that add another layer of complexity to the already intricate physical processes shaping the comet's remarkable asymmetric tail. The moment of observational revelation arrives as ground-based and space-based telescopes around the world focus their collective attention on 3I/Atlas, capturing with unprecedented detail and clarity the full extent of the symmetry-breaking phenomenon that has been building throughout the comet's approach to the inner solar system. This coordinated international effort, involving dozens of observatories and hundreds of astronomers working across multiple time zones and wavelength regions, represents one of the most comprehensive observational campaigns ever mounted to study a single comet. Driven by the recognition that 3I/Atlas offers a unique opportunity to witness and understand asymmetric tail formation in an interstellar visitor with properties unlike any previously observed solar system object. The Hubble Space Telescope, with its exquisite resolution and freedom from atmospheric turbulence, provides the sharpest images of the comet's inner coma structure, revealing intricate details of jet formation and dust distribution that remain invisible to ground-based observers. These images, processed with sophisticated enhancement techniques that bring out faint structural features, show a complex network of intersecting plumes, spiral patterns, and curved streamers that trace the three-dimensional flow of material away from the nucleus in patterns that violate every assumption of radial symmetry built into classical comet tail models. Large, ground-based telescopes equipped with adaptive optics systems achieve image quality approaching space-based observations while providing the light-gathering power necessary for detailed spectroscopic analysis of the faint emission lines produced by trace molecular species throughout the coma. The 10-meter Keck telescopes in Hawaii, the 8.2-meter Very Large Telescope Array in Chile, and the 10.4-meter Gran Telescopio Canarias in the Canary Islands work in coordinated observing programs that track the comet continuously as Earth's rotation carries different facilities into optimal viewing positions. Radio telescope observations reveal the presence and distribution of molecular species that emit at millimeter and sub-millimeter wavelengths, providing unique information about the cold outer regions of the coma, where optical emission lines are too weak to detect. The Atacama Large Millimeter Array, with its unprecedented sensitivity and resolution at these wavelengths, maps the three-dimensional distribution of carbon monoxide, water vapor, and other molecules throughout the tail with precision that reveals subtle asymmetries in gas kinematics and chemical composition that complement the optical observations. Space-based infrared observatories, including the Spitzer Space Telescope and the James Webb Space Telescope, provide thermal imaging that reveals the temperature distribution and size segregation of dust particles throughout the tail structure. These observations show systematic temperature variations that reflect particle size differences and radiation heating effects, confirming theoretical predictions about how different-sized grains respond to solar heating and radiation pressure forces. The infrared data also reveal the presence of complex organic compounds and silicate minerals that produce characteristic spectral features at these wavelengths. The integration of observations across the electromagnetic spectrum creates a comprehensive view of the comet's asymmetric tail that no single observational technique could achieve independently. Optical images show the overall morphology and brightness distribution. Ultraviolet spectroscopy reveals the ionized gas component and plasma physics processes. Infrared observations trace thermal emission from dust particles and molecular vibrational transitions. And radio measurements map the distribution and kinematics of neutral molecules throughout the extended coma. Time-resolved observations reveal the dynamic evolution of asymmetric structures within the tail as new material continues to flow outward from the nucleus while previously released gas and dust travel along their divergent trajectories under the influence of radiation pressure, magnetic fields, and gravitational perturbations. High-cadence imaging shows how individual features within the tail structure rotate, expand, and interact with each other over timescales ranging from hours to weeks, providing direct observational evidence for the complex multibody dynamics that govern particle motion in the cometary environment. Polarimetric observations provide additional constraints on particle properties and three-dimensional structure by measuring how the scattered light from dust grains varies with viewing angle and wavelength. The degree and direction of polarization depend on particle size, shape, composition, and spatial orientation in ways that can be modeled theoretically and compared with observations to infer physical properties that cannot be determined through photometric measurements alone. These polarization data reveal systematic variations throughout the tail that reflect the size, segregation, and compositional gradients established by the various physical processes operating on different particle populations. Spectropolarimetry. Combining spectroscopic and polarimetric techniques reveals how the polarization properties vary with wavelength in ways that provide detailed information about particle composition and structure. Silicate dust grains produce polarization signatures that differ systematically from those of organic particles or metallic inclusions, allowing observers to map the distribution of different material types throughout the tail structure. These observations confirm the presence of interstellar dust components with properties distinct from typical solar system materials, providing direct evidence for the comet's extrasolar origin. Astrometric measurements of particle positions and motions within the tail structure provide quantitative data on particle trajectories that can be compared directly with theoretical predictions of radiation pressure effects, gravitational perturbations, and magnetic field interactions. These positional measurements, precise to fractions of an arc-second despite the comet's distance of hundreds of millions of kilometers, reveal systematic deviations from simple ballistic trajectories that confirm the operation of the various non-gravitational forces predicted by theory. The observational campaign extends beyond professional observatories to include contributions from amateur astronomers around the world who monitor the comet's brightness variations, photograph its changing appearance, and provide continuous coverage that fills gaps in professional observing schedules. This citizen science component proves crucial for detecting rapid variability and short-lived features that might be missed by the more limited observing time available at major facilities. Coordinated observations from multiple sites provide the temporal coverage necessary to study phenomena that occur on timescales shorter than Earth's rotation period, ensuring that no significant changes in comet behavior go unobserved. This global network approach proves essential for understanding the rapid evolution of asymmetric features and the correlations between different physical processes operating simultaneously throughout the comet's environment. The data analysis challenge posed by this wealth of observational information requires sophisticated computational techniques and international collaboration among research groups with different areas of expertise. Image processing algorithms designed specifically for cometary observations enhance faint structural features while preserving quantitative photometric accuracy. Spectroscopic analysis software extracts physical parameters from complex emission line profiles that reflect the superposition of signals from gas and dust moving at different velocities throughout the three-dimensional coma structure. Statistical analysis techniques applied to the observational datasets reveal correlations and patterns that might not be apparent in individual images or spectra, providing insights into the underlying physical processes that create and maintain the observed asymmetric structures. Principal component analysis, wavelet transforms, and other mathematical tools help identify the dominant modes of variability and the physical parameters that control the comet's behavior over different timescales and spatial scales. As the observational revelation unfolds through months of intensive study, the accumulated evidence establishes beyond doubt that 3I/8less represents a new class of cometary object whose asymmetric tail formation challenges fundamental assumptions about comet physics and provides unprecedented opportunities for advancing theoretical understanding of the complex processes that govern small body behavior throughout the solar system and beyond. The theoretical community struggles to reconcile the unprecedented observations of 3I/Atlas's asymmetric tail with existing models of comet physics as computational simulations and analytical theories that have successfully explained decades of cometary phenomena, fail to reproduce the complex structural features and temporal evolution documented by the International Observational Campaign. This theoretical crisis, though initially frustrating to researchers who have devoted careers to understanding comet behavior, ultimately drives innovative advances in computational techniques, physical modeling approaches, and fundamental understanding of the multi-scale processes that govern dust and gas dynamics in the unique environment surrounding active comets. Classical comet tail models, developed over the past century and refined through application to hundreds of observed comets, rely on fundamental assumptions of spherical symmetry, uniform surface properties, and simple force balance between solar gravity and radiation pressure that determine particle trajectories in predictable ways. These models successfully explain the basic morphology and evolution of typical comet tails, including their characteristic curved shape, the size segregation of dust particles, and the temporal variations that correlate with heliocentric distance and solar activity levels. However, when applied to 3I/Atlas, these traditional approaches produce smooth, symmetric tail structures that bear little resemblance to the complex asymmetric phenomena actually observed. Computational fluid dynamics simulations that attempt to model the three-dimensional gas flow from multiple active regions on an irregularly shaped, rotating nucleus encounter numerical challenges that push the limits of available computing resources and algorithmic sophistication. The wide range of physical scales involved, from molecular collisions near the nucleus surface to tail structures extending millions of kilometers into space, requires adaptive mesh techniques and multi-physics coupling that strain the capabilities of even the most powerful supercomputers. Initial attempts to incorporate realistic nucleus topography, non-uniform surface composition, and time-variable activity patterns produce results that capture some aspects of the observed asymmetry but fail to reproduce the detailed structure and temporal evolution documented by observers. The dust dynamics component of theoretical models faces particular challenges in treating the size-dependent response of particles to radiation pressure while accounting for the complex initial velocity distributions imparted by gas drag from non-uniform jet activity. Traditional approaches that assume simple radial expansion from a point source must be replaced by three-dimensional particle tracking algorithms that follow millions of individual dust grains as they respond to the full vector field of forces, including solar and planetary gravity. Radiation pressure that depends on particle size and optical properties, and Lorentz forces from magnetic field interactions with charged dust components. Plasma physics models that describe the interaction between solar wind and cometary ions encounter difficulties in treating the boundary conditions and coupling between neutral gas dynamics and charged particle behavior in the highly inhomogeneous environment created by asymmetric outgassing. The standard magneto-hydrodynamic approximations that work well for typical comet-solar-wind interactions break down in regions where the plasma density varies by orders of magnitude over spatial scales comparable to particle gyroradii, requiring kinetic plasma simulations that track individual particle trajectories through self-consistently computed electromagnetic fields. The chemical kinetics models that predict molecular abundance ratios and photochemical processing throughout the coma must be extended to account for the temperature and density gradients created by non-uniform gas expansion from discrete jet sources. Reaction networks that assume chemical equilibrium or simple steady-state balances between production and destruction processes fail to reproduce the observed spatial variations in molecular abundances and excitation conditions, necessitating time-dependent chemical models that follow the evolution of gas parcels as they expand outward and experience changing physical conditions. Advanced numerical simulations that attempt to couple gas dynamics, dust particle tracking, plasma physics, and chemical kinetics into comprehensive multi-physics models encounter computational requirements that exceed the capabilities of current supercomputing facilities. Hybrid approaches that treat different physical processes with different levels of approximation show promise for capturing the essential physics while remaining computationally tractable. But these methods require careful validation against observational data to ensure that the approximations do not eliminate crucial physical effects. Machine learning techniques applied to the observational datasets offer potential pathways for identifying patterns and correlations that might guide the development of improved theoretical models. Neural network algorithms trained on large databases of comet images can potentially identify morphological features and evolution patterns that human observers might miss. While statistical analysis of spectroscopic data may reveal chemical signatures that constrain physical conditions throughout the coma in ways that complement traditional modeling approaches, the theoretical challenges posed by 3E/Atlas drive the development of new mathematical techniques for treating multi-scale, multi-physics problems that arise throughout astrophysics and planetary science. Adaptive mesh refinement algorithms that concentrate computational resources in regions where rapid spatial variations occur. Implicit-explicit time integration methods that handle processes with vastly different characteristic timescales, and parallel computing strategies that efficiently distribute calculations across thousands of processor cores represent advances that benefit the broader computational science community. Analytical theory development focuses on identifying the key physical parameters and dimensionless ratios that control the transition from symmetric to asymmetric tail behavior. Seeking scaling laws and similarity solutions that provide physical insight into the complex numerical simulation results. Perturbation theory approaches that treat asymmetric effects as small departures from symmetric base states show limited success for 3Y/Atlas, where the asymmetries are large and qualitatively different from symmetric solutions rather than small corrections to them. Laboratory experiments designed to study scaled versions of cometary outgassing and dust entrainment processes provide controlled environments where specific aspects of the theoretical models can be tested and validated. High vacuum chambers equipped with sublimating ice surfaces, particle injection systems, and laser diagnostic techniques allow researchers to investigate gas-dust interactions, radiation pressure effects on microscopic particles, and plasma formation processes under conditions that approximate cometary environments at reduced spatial and temporal scales. The interdisciplinary nature of the theoretical challenges requires collaboration between researchers with expertise in fluid dynamics, plasma physics, chemical kinetics, celestial mechanics, electromagnetic theory, and computational mathematics. This collaboration leads to cross-fertilization of ideas and techniques between different scientific disciplines and drives the development of integrated modeling frameworks that can address complex multi-physics problems throughout the physical sciences. International workshops and conferences focused on the theoretical implications of 3I/Atlas observations bring together leading researchers from around the world to share results, discuss challenges, and coordinate research efforts. These collaborative activities accelerate progress by avoiding duplication of effort, facilitating the sharing of computational resources and expertise, and ensuring that different research groups build upon each other's work rather than pursuing isolated approaches. The theoretical crisis created by 3Y/Atlas ultimately proves beneficial for the field of comet science by forcing researchers to confront the limitations of existing models and develop more sophisticated approaches that can address the full complexity of cometary phenomena. The new theoretical frameworks and computational techniques developed to understand this remarkable interstellar visitor will prove applicable to future cometary observations and contribute to broader advances in understanding small body physics throughout the solar system. The ongoing struggle to develop adequate theoretical models for the 3I/Atlas represents a classic example of how exceptional observations can drive scientific progress by revealing the inadequacy of existing theoretical frameworks and motivating the development of new approaches that expand the boundaries of scientific understanding. As computational capabilities continue to advance and observational techniques become even more sophisticated, the theoretical community gradually develops the tools necessary to understand and predict the complex asymmetric phenomena that make this interstellar comet such a remarkable and scientifically valuable object. The cosmic archive continues its patient journey deeper into the solar system as 3I/Atlas carries its ancient story past the orbit of Venus, its asymmetric tail now stretching for millions of kilometers in a gossamer display of broken symmetry that captures the imagination of observers worldwide while simultaneously challenging the theoretical understanding developed over decades of cometry research. This interstellar messenger, born in the molecular clouds surrounding distant stars billions of years ago, has traveled across the galaxy to provide astronomers with an unprecedented opportunity to witness the complex physics of comet tail formation under conditions never before encountered in solar system objects. The tail streams behind the comet in graceful curves that reflect the intricate interplay between multiple physical processes operating simultaneously across vast ranges of spatial and temporal scales. Each microscopic dust grain follows its individual trajectory, determined by the precise balance between solar gravity, radiation pressure, and magnetic field interactions. Yet, collectively, these countless particles create coherent structures that persist for weeks and months as they travel outward through interplanetary space at velocities that will eventually carry them beyond the gravitational influence of the Sun and back into the interstellar medium from which their parent comet originated. The perpetual nature of the asymmetry has become the defining characteristic of 3I/Atlas's appearance, as months of continuous observation revealed that the complex structural features in the tail do not represent transient phenomena that appear and disappear unpredictably, but rather stable patterns that evolve gradually in response to the changing physical conditions as the comet approaches perihelion. The spiral patterns traced by dust released during different rotational phases of the nucleus, the systematic size segregation that creates distinct zones within the tail structure, and the magnetic field effects that deflect charged particles along field lines all contribute to a display of cosmic architecture that maintains its essential asymmetric character despite continuous evolution in detail and structure. The brightness distribution throughout the tail reveals the complex history of mass loss from the nucleus as material released weeks and months earlier continues to scatter sunlight back toward Earth-based observers, while new dust and gas streams outward to join the expanding envelope. The brightest regions correspond to areas of highest particle density where recent outgassing has concentrated material along specific trajectories, while fainter extensions trace the paths followed by older material as it disperses under the influence of radiation pressure and gravitational perturbations. This temporal stratification creates a three-dimensional record of the comet's activity history that can be read like geological layers in terrestrial rock formations. The chemical composition of the tail material preserves information about conditions in the interstellar medium where 3I/Atlas formed, with isotopic ratios and molecular abundance patterns that reflect the nuclear processes operating in stellar cores and the chemical evolution of the galaxy over cosmic time. As spectroscopic observations continue to map the distribution of different molecular species throughout the expanding gas envelope, they reveal gradients and variations that provide insights into the thermal and chemical history of the comet's nucleus during its billion-year journey through space. The size distribution of dust particles throughout the tail follows power law relationships that appear universal among cometary objects. Yet 3I/Atlas displays subtle deviations from these standard patterns that may reflect the unique conditions of its formation in an extrasolar environment. The largest particles, those that dominate the visible brightness of the tail, show mineral compositions that include crystalline silicates and organic compounds processed by stellar winds and supernova shockwaves that operated in the comet's birth environment. These materials carry within their crystal structures the isotopic signatures of nucleosynthesis processes that occurred in stars that lived and died long before our solar system began to form. The magnetic field interactions that contribute to the tail's asymmetric structure continue to evolve as the comet encounters different configurations of the interplanetary magnetic field embedded in the solar wind. Each change in field orientation creates corresponding changes in ion acceleration patterns and plasma flow directions, leading to temporal variations in tail morphology that provide real-time demonstrations of magnetohydrodynamic processes operating in the tenuous plasma environment of interplanetary space. These magnetic effects extend far beyond the visible portions of the tail, creating invisible structures in the solar wind wake that can be detected by spacecraft instruments hundreds of millions of kilometers downstream from the comet. The gravitational influences of planetary bodies throughout the solar system continue to exert subtle but measurable effects on dust particle trajectories as the expanding tail material encounters the complex gravitational landscape created by Jupiter's massive presence and the collective influence of smaller planetary bodies. These perturbations accumulate over months and years to create systematic deflections that will eventually scatter comet material throughout the solar system, contributing to the zodiacal dust complex and potentially delivering interstellar organic compounds to planetary surfaces, including Earth. The observational legacy of 3Y/Atlas extends far beyond the immediate scientific discoveries made during its passage through the inner solar system. The comprehensive dataset created by coordinated observations across multiple wavelengths and from numerous facilities represents an unprecedented archive of information about asymmetric comet tail formation that will support theoretical research for decades to come. Each image, spectrum, and photometric measurement contributes pieces to a complex puzzle that reveals the intricate physics governing small body behavior in the solar wind environment. The technological innovations developed to observe and analyze 3I/Atlas's complex structure drive advances in astronomical instrumentation and data processing techniques that benefit the broader astronomical community. New image processing algorithms designed to enhance faint structural features in comet tails find applications in studying galaxies, nebulae, and other extended astronomical objects. Spectroscopic analysis techniques developed to extract chemical information from complex line profiles prove useful for stellar astronomy and exoplanet atmospheric studies. The computational methods created to model multiphysics processes in cometary environments contribute to advances in plasma physics, fluid dynamics, and celestial mechanics. The international collaboration that emerged to study this remarkable object demonstrates the power of coordinated scientific effort in addressing complex research challenges that exceed the capabilities of individual institutions or nations. The sharing of observational data, computational resources, and theoretical insights accelerates scientific progress and establishes precedents for future collaborative projects that may address even more ambitious questions about the nature and evolution of the universe. The educational impact of 3I/Atlas extends to students and amateur astronomers worldwide who follow its progress through online resources, public lectures, and citizen science projects that engage the broader community in scientific discovery. The comet's spectacular appearance and interstellar origin capture public imagination in ways that connect people to the cosmic perspective and inspire interest in science, technology, engineering, and mathematics careers among young people who will shape the future of scientific research. The philosophical implications of studying an object that originated in another stellar system raise profound questions about the distribution of organic compounds throughout the galaxy, the potential for life to arise in diverse environments, and the interconnected nature of cosmic evolution that links the chemistry of distant stars to the materials from which planets and potentially life itself can form. The complex organic molecules detected in 3I/Atlas's coma represent a direct sample of interstellar chemistry that may have played crucial roles in the origin of life on Earth and other worlds throughout the galaxy. As 3I/Atlas continues its hyperbolic trajectory that will eventually carry it back into interstellar space, it carries with it not only its own ancient record of cosmic history, but also the expanded human understanding of cometary physics that its study has made possible. The asymmetric tail that makes this comet so scientifically significant represents more than just a departure from expected behavior. It provides a window into the complex multi-scale physics that governs matter and energy throughout the universe. The perpetual streaming of the asymmetric tail serves as a reminder of the dynamic nature of the cosmos, where matter and energy flow continuously through space and time, creating structures of extraordinary beauty and complexity that reflect the operation of fundamental physical laws under conditions that challenge theoretical understanding and inspire new discoveries. In the gentle curves and spiral patterns of dust and gas streaming away from this ancient nucleus, astronomers see not just the end result of specific physical processes, but a manifestation of the creative power of natural laws to generate order and structure from the apparently chaotic dance of matter and energy in the vacuum of space. The comet drifts onward through the cosmic dark, its tail streaming in eternal asymmetry behind the ancient nucleus that has crossed the vast emptiness between stars. The dance of dust and gas continues with patient precision, each particle following paths determined by forces that operate with mathematical certainty across the immensity of space. Time moves differently here, measured not in human moments, but in the slow sweep of gravitational orbits and the gradual dispersal of matter into the interplanetary medium. The asymmetric patterns that captivated observers slowly fade as distance and dispersion claim the gossamer structures, but the physical processes that created them continue with quiet persistence. Radiation pressure still pushes microscopic grains away from the sun. Magnetic fields still guide charged particles along invisible pathways. Gravity still curves trajectories through dimensions too large for terrestrial comprehension. The universe continues its ancient work of moving matter and energy through space, creating temporary arrangements of extraordinary complexity before returning all things to the fundamental simplicity of scattered atoms drifting in the void. Somewhere in the depths of interstellar space, other nuclei of ice and rock drift in the darkness between stellar systems, carrying their own chemical archives and awaiting their own eventual encounters with distant suns. The story of 3I/Atlas becomes part of a larger narrative written in the patient language of cosmic time, where billions of years pass like seasons and the asymmetric beauty of a comet's tail represents just one brief moment in the endless evolution of matter and energy throughout the universe. The broken symmetry fades into memory, but the fundamental forces that created it remain eternal, ready to write new stories of complexity and beauty in the infinite darkness of space.